In this course, you've got access to the compiler. Now, we're not going to cover the compiler until Design a CPU 5, which will be the next course. So on the next course, we will cover the compiler, the assembler, the linker, and any other sundry software which we haven't covered so far within the rest of the courses. So you have access to this now, and if you head into the folder Tools, Compiler, and you'll see the files here: compile, generate, node, parser, tokenizer. Now, the compiler was generated by Timothy Morgan. Now, on the next course, we will use his compiler, and we will also cover the theory of compiler design, but we'll have his compiler there as an access to an actual functioning and working compiler. So let's have a look at the examples that we have here. So if you notice the folder called RMG, this is going to contain all of the high-level language files. So there's already a few in there at the moment. So we can click on this here, and we can note here that we've got some include files. So this folder here contains all of our library files. So there's the BIOS, the graphics, the maths, and the string library. But we'll talk about that whenever we cover the actual compiler in the next course. So let's pick out one of these. So we've got the plot sign.rmg. So if we come in here and click on this, so this is our high level language, and we'll talk our way through this quickly. So we're going to draw the sign on the graphics screen using this code. So we do what we would normally do, for example, within a C or C++. We've got our hash include, and we've got the files maths.lib and graphics.lib, because we need the subroutines within these libraries in order for this code to run. And then we've got the main body of our code, which is the void main, and we've got the open and close our curly brackets. So we're going to set aside the x, y, and angle variables, and they're going to be floating points. And we're going to have an integer variable I in order to do the count. We're going to start off at the x position -127 on the screen. And we're going to run from I is equal to 0 to 255 in steps of 1. So this will cover the entire width of the screen. Now we're going to do the plot, and you can see that we've got the double backslash, which tells us it's a comment. So we're going to define an angle, so this will be the angle in radians. And then we've got our function, y is equal to float_sign, and we're going to pass the angle into this function. And then when we get the output, we're going to multiply that value by 50. And then we're going to use the fplot command, which exists within the graphics library, and this one here, the float_sign, exists within the mathematics library. So we're going to plot this off, so there's going to be an x position, a y position, and a colour, and then we're going to add 1 on to the value of our input, so this becomes 1 upon the 20.21267. So we keep adding 1 on, and all we're doing there is increasing the value of the input in radians. So this is the final code, and we can compile it. So we can go terminal, run task, and we can compile file. And we'll check and see everything that comes up in our window here. So you can see here, compiling plot.plotSign.rmg, and it's tokenizing, parsing, generating, and it says compilation successful. So after we've gone through the compilation, we then have to go through the assembly. So it's now assembled it, and it's come up with assembly successful. So if we were to drop into the file just above, you'll see it will generate a file called .asm. So this will be our intermediate assembly file. So if we click on this and we check it, we can see it's got the auto-generated assembly code for this program. Now we've got our assembly code here. This is auto-generated. Now I'm not going to talk through it, but obviously the auto-generated assembly code is most probably not as efficient as in the assembly code that we will have written in order to do this plot, but we're not interested in that for the moment. So we can also go in and we can have a look at the machine code. So we've got plotSign.asm, and we should have the machine code for it. So we go to machine code and go down to plot. So plotSign machine code, and here is the machine code for that program. So we're now ready to load this machine code. In fact, what we will do is, rather than loading it into the machine, we'll run it on the emulator, because we're going to get a very quick output from the emulator. And after we see it works on the emulator, we can put it on the machine and we can test it out on the machine. So if we open up our plotSign.asm, we can go to the terminal, run task and emulate file. So we can see it's executing the emulate the plot sign, and then we can type our R to run it, and then we can do GD for graphics dump. So now we can go in and we can load our file into the graphics 2. So we go edit, open, and we find our graphics.dat file, and you can check and see whether we've got values in here, and you can see some of the values here. And then we're going to have to go into the ROM, and we can open up our splash screen. So we've got machine code and we're looking for splash. Close the window, design, user panel, and simulate, tick enabled. So that's it running through now, and it will work its way all the way down here until it gets to FF. And as it finds each value, it will plot that value to the screen. So we'll have a look at the screen, and what I'll do is I will fast forward this and I'll get you at the end of the simulation. The simulation should take about a couple of minutes. So that's us emulated the sine function. Now what we can do is we can stop this, we can reset it, and we can actually load the program directly into the RAM. So edit contents, open. Now we're looking for our plot sign So we head up here. It's going to be plot sign MC, so we can open it up directly. We can close it, and now we can actually run it directly here. So now, rather than run the emulated version and just print off the splash screen, we're actually running through within our CPU. Now it will take a considerably longer length of time to render all of the points, so possibly 45 minutes or an hour before we get all of the points. In fact, most probably longer than that. But we can expect to get the same output that we got whenever we looked at the emulator. So again, I will fast forward this and we'll see what the final result is. So it is still running and it's produced the first few points. So it's going to produce the curve from left to right in this direction. Now I've got one that I created earlier. So let's open this up and we'll have a look. So this is one that I simulated previously, and this is the final outcome. So what we've seen here is the full design cycle, from a high level language to the compilation, and then the assembly and the linking, and finally to the machine code. We've worked through an emulation, and we've also worked through the rendering actually within the CPU. So we've really got to the end of exactly what it is we want to do with this entire suite of courses. But of course, we haven't actually described or defined or actually looked at how the compiler, the emulator, the assembler and the linking actually happens. So the final course, Design a CPU 5, will cover all of that. So thank you for listening. I'll get you on the next video. Goodbye.